So let's go ahead and take a quick look at how we could use these ideas of dilations in a few example problems. For this problem, we have triangle A prime, B prime, C prime, D prime, which is a dilation with a center at P of the black triangle ABCD. So we can see that it's obviously an enlargement, right? That the black triangle got bigger. The question is just asking, how are the side lengths and angle measures of the two triangles compared to each other? So let's look at side lengths first. Let's think about the four sides of this one and the four sides of this one. The side lengths on the black triangle are 3, 2, 3, and 2. But if I look at the side lengths on the enlarged triangle, it looks like it's 1, 2, 3, 4, 5, 6, 7, 8, 9. So we got 9 on this side. We got 6, we got 9, and we got 6. So I can see that each time this side, all four of these sides got tripled in length. 3 times 3 gave me 9, 2 times 3 gave me 6, 3 times 3 gave me 9, and 2 times 3 gave me 6. So the side lengths of A prime, B prime, C prime, D prime are all 3 times the length of the side lengths of the original rectangle ABCD. And what that tells us is this enlargement actually has a scale factor of 3, right? This is an enlargement with a scale factor of 3. And how do I know that? I know that because if I take AB and multiply it times 3, that gives me the length of A prime, B prime. And if I take BC and multiply it by 3, that gives me B prime, C prime. And CD times 3 gives me C prime, D prime. And AD times 3 gives me A prime, D prime. So it's an enlargement with a scale factor of 3. Now it also asks about the angle measures. And for this, we can just remember that we learned one of the properties of dilations is that the angle measures don't change. So if this was a rectangle, we know that angle A is 90 degrees, and angle A prime will still be 90 degrees. Angle B is 90, angle B prime will still be 90. None of the angle measures will change because dilations preserve angle measure. Our second example here shows us another dilation. J prime, K prime, L prime, M prime is a dilation of JKLM. So we started with the black figure, we dilated it, ended up with the red figure here. And the question is, this dot here is just the center of dilation. The question is, what's the scale factor? And we'll notice that LK went from being 12 units long to 18 units long. So LK times the scale factor turns into L prime, K prime. So 12 times the scale factor turns into 18. So to find that scale factor, I can just divide each side of this little equation by 12, and I get 18 over 12, which is equal to 1.5. So the scale factor for this dilation would be 1.5. Everything on the red shape is 1.5 times the length of its corresponding part on the black shape. In this third example, we are being asked to actually perform a dilation. It says, what are the vertices of the dilation by a scale factor of 3 of triangle ABC? And notice it didn't tell us what the center of dilation is, so that means that we're assuming that that center of dilation is the origin right here. So we have to move each corner of this according to these instructions. So the first thing I'm going to do is I'm actually going to kind of draw in the rays that these points are going to slide along as we perform this dilation, right? These points are going to each slide along these different rays connecting the center of dilation to the actual points. So point A is going to slide along this ray, point C is going to slide along this one, point B is going to slide along this one here. And the way they're going to slide until they get 3 times as far away from the origin as where they are now. So let's start with C. C, we can see it's 3 units away from the origin. It's right along the x-axis here. It's 3 units away from the origin. So it's going to slide 3 times as far. So it's going to end up out here at 9. C prime will end up out there at 9, comma 0. That one's pretty easy because it's just kind of sliding horizontally. These other two, A and B, are sliding along these rays in a more diagonal fashion. So we got to think about, how am I going to get this? Where do I need to stop to where I'm 3 times as far away from the origin as where it is now? Well, I like to think about this not in terms of a diagonal movement, but a combination of a horizontal movement and a vertical movement, a downward vertical movement in this case, to get to A. To get to A, I have to move 2 units to the right and 1 unit down. If I triple both of those amounts, that would be equivalent to moving 3 times as far diagonally. So again, instead of moving 2 units to the right and 1 unit down, I'm going to move 6 units to the right and 3 units down, and I'm going to end up right there at that location, 6, negative 3. So that is going to be 6, negative 3. It went from being 2, negative 1 to 6, negative 3. C prime went from being 3, comma 0 to 9, comma 0. Now what about B? B is at negative 1, comma 2. Well, to get from origin to B, I have to move right 1 unit and up 2. Now I'm just going to triple both of those movements. I'm going to move right 3, and I'm going to move up 6, and that's going to take me to this point right there. So B prime is right up here at negative 3, comma 6. And so our new vertices of the dilated triangle, A prime is going to be 6, negative 3, B prime is negative 3, 6, and C prime is 9, comma 0. And our triangle, if we wanted to kind of sketch our triangle in here, it's going to look about like, so there's A prime down there, connect that over to C, and connect B prime and C prime, and there we have our triangle. Okay, so in this problem now we're going to do another dilation, but this time it's going to be a reduction. I know it's going to be a reduction because the scale factor is less than 1. Now, for a second here, let me think about that last example I did where I took A, B, and C. A was at 2, negative 1. B was at negative 1, 2. And C was at 3, comma 0. And I enlarged by a scale factor of 3. And the places they went to, look at this. It went to 6, negative 3, negative 3, 6, and 9, comma 0. Now some of you might have noticed something about what these numbers became from what they started at, and the relationship between these numbers, the scale factor, and these numbers. If I take 2 times 3, I get 6. If I take negative 1 times 3, I get negative 3. Negative 1 times 3 is negative 3. 2 times 3 is 6. 3 times 3 is 9. 0 times 3 is 0. It's kind of interesting, right? It seems that I can take each part of these coordinates, multiply by the scale factor, and the result will be our image coordinates. Let's see if we can do that same idea to these coordinates, these vertices of this quadrilateral. So W is at 2, negative 2, and our scale factor on this one is 0.25, which is 1/4. So that would tell me that W prime will end up at, let's see, what's 2 times 0.25? Well, that would be 0.5, or 1/2. So W prime would be 0.5, negative 0.5. X is at negative 4, comma 2. So it would move to X prime, which again, negative 4 times 0.25 is going to be negative 1. So we're looking at negative 1 and then 0.5. Y is at 0, comma 4. So that's going to move to Y prime, which is still going to be 0 because 0 times 0.25 is still going to be 0. And then 4 times 0.25 will be 1, so it's at 0, comma 1. And then Z, which is currently at 4, comma 2, that's going to move to Z prime, which will be at 1, comma 0.5. So here are the 4 new coordinates of our quadrilateral after we dilate it by a scale factor of 0.25, again centered at the origin since it doesn't list a different center of dilation. Now in this final example, unfortunately, that shortcut that we used in the last one is not going to work because our center of dilation is not the origin in this problem. We can see that the center of dilation now is going to be point R. All right, so we have to dilate by a scale factor of 1/2. So this is going to be a reduction. Our new rectangle, looks like this is a rectangle with 4 right angles. Our new rectangle is going to be smaller than QRST. So let's take a look. Its center of dilation is R, and it needs to dilate by a scale factor of 1/2. Well, let's think about point R. One of the properties we learned about dilations is any point that is actually on or is the center of dilation will not move after the dilation is performed. So that means that R is currently at -2, 7, and it's going to remain at -2, 7. So nothing's going to change there. S, let's look at S. S's current location is at 4, 7. Where is it going to go? Well, it's going to get connected to R, right? We have this ray that's like this rail that point S is going to slide along. And since this is a reduction by 1/2, it's going to slide towards R. It's going to shorten the distance from R to where it is now. And it's going to shorten it so that it's only half as far away. So how far is S currently away from R? Well, it's 1, 2, 3, 4, 5, 6 units away. If we cut that in half, it would be 3 units away from R. So if I'm here and I go only 3 units along this ray, I would end up right there. So that's where S prime will be. S prime is going to be at the location 1, 7. How about Q? Let's talk about Q. Q is currently at -2, -1. And that we can see is, well, let's kind of draw that little ray that represents the rail. I think of it as like a rail that point is going to slide along. And currently it is, let's see, what is that, 8 units away from R. So it's going to slide to a point closer to R that's only half as far away from where it is currently. So that would put it right there, halfway. So Q prime will now be right there. And that location, it looks like, is -2, 3. And so that just leaves T. And the way we're going to figure out T, I'm going to do it this way. I'm going to use the idea that when I perform a dilation, angles won't change. So, for instance, angle RST is a 90-degree angle. That tells me that angle RS prime T prime also needs to be a 90-degree angle. So T is going to be straight down below S prime. Then we can say the same thing about angle RQT being a 90-degree angle and RQ prime T prime needing to stay a 90-degree angle. So T prime will be straight over to the right from where Q prime is so that we maintain this 90-degree angle. So if I go straight over from Q prime and straight down from S prime, that location would be right there. So T prime is going to be right here. T is going to go from being at 4, -1 to T prime at, let's see, what is that? 1, 3. And now we can kind of see where the 4 corners of our new rectangle will be. Each corner is half as far away from R as where it used to be. S used to be 6 units away, now it's 3 units away. Q used to be 8 units away, now it's 4 units away. And we can also kind of look, just to show you another way we could have found the location of T prime. To get from R to T, I had to go over 6 and down 8. Well, if I only go half those distances, I would go over 3 and down 4, and you can see we're going to end up right there where we put T prime.